So hello everyone again. Now I started recording, and this is the 5th workshop, which will be about dealing with geometry in DX11, and yep, it will be probably a longer one because there's a lot to cover with that thing. So we will start right away if I clear my clutter on the desktop. So we don't need this and this, and I put it here, put the obvious here. Don't need this, and where's the, oh, here you go, there's the chat. So hello people. I will also turn off the intro patch. Sorry, yeah, it's obvious thingy. Can I this up? Yep. So there you go. So after this pretty clumsy intro, I mean the pretty clumsy introduction of the starting of the workshop, so we can start right away. So first of all, this workshop I thought about, I will first cover how to convert from DX9 to DX11 workflow. Well, not workflow, but with geometry wise, because there are still a couple of people who is afraid to do that, and this will be for them. And so that will take up, I don't know, roughly 20 minutes. So if you already know that, you can come back later, like 20 minutes later, and that will be, we will start doing more interesting stuff. Yup. Also, I don't know, oh yes, I forgot to turn on a lamp. And also, after that, we will dive into what can be done and what is the geometry in the DX11. Maybe I will tell that in the first part though. And also what will be what it can be used for. So not just geometry. You surprise, not just models, not just meshes. And the third part, we will dive into a little bit of shading thingies and a couple of ways how you can develop thingies. Oh yeah, it's yeah, actually not my haircut, my beard. That was my beard cut away because my lady done that. Anywho, I will quit this because this eats up a lot of CPUs. Yeah, save all. And let us start with a fresh VVV window. Oh yeah, I closed the window as well because it is super crazy. Trains are super loud. So, fresh patch. Let's start it here, and after a little bit of mangling, we will start up. Waiting time. Yeah. So this is also why it's opening. I will also tell you that this is the first episode as a sub-series of the weekend workshops, and there are a couple of misunderstandings about that. So that is this will be 4 parts: geometry, pixel shaders, and instance noodles, so higher level thing on geometry, and then finally MSH. And yeah, why is it taking this long? Is it? Oh, there you go. Yeah, this is just for the Kinect lead. Yep. So, what you used to do in DX 9, first of all, what was the geometry in DX 9 is you had this mesh, and which you had a vertex buffer, and it all happened on the CPU, and this was simple. And you had like fixed semantics. You could fill it up, fixed data. So that was a pretty simple pipeline in DX 9, and you had a couple of nodes which helped you on the way if you missed some data. And also you had the index buffer here to optimize the amount of vectors you have to store, which is still present in DX 9, but not in the processing of the geometry. So DX 9 you can still read, DX 11 you can still read index buffered geometry, but not. But when you process it, it will actually just spit out lots of triangles sequentially. So first difference is, compared to DX 9, the data is stored on the GPU. And now let's just, while I'm doing the renderer, I will just explain that. So in DX 11, the geometry part is pretty it's a pretty dumb thing. It's just a stream of bytes basically with a little bit of metadata which tells the shader and tells the input assembler that what it have to do with the data, or which part of the vertex means what, which semantics. So it is very much more free to do stuff with geometry in DX 11 than in DX 9, as you could expect. Let's see what we should start with. So let's have this, and let's have a simple quad just to, which is also geometric here. So how could I present that though? Yeah, you could expect something like this. We had a nice quad here. So in the format of the data, the format of a vertex in the DX 11 is called the input layout, because for reasons I'm not sure. I have a guess, which might be because of the input assembler and and reasons, I don't know. So input layout, and as you can see, it spits out as 3 input elements, which is basically just a structure of a couple of data, which describes us the semantics, which we will access in the shader later on. So the shaders access it. Well, the vertex shaders and geometry shaders access it using this semantics. And here you can see how many components it has, which is given in DXGI formats. Well, the format string. So the 4 component will have like RGB, 32-bit float, similar to what we had in textures, which will be covered next workshop. So here's the semantic name, semantic index, which is a little number after this which will be present in the shader with a number after this name. So like this text code 0, and then we have this offset. So this is byte offset. I will cover this a little bit later on the shader part, but don't be afraid of that. This is just tells us that in the stream, in a vertex, how much, which byte or data starts. So which byte the position starts, which byte the normal starts, and which byte the texture coordinate starts. And you can see here the position. So because it's a 32-bit number, 32-bit floating point number, it takes up 4 bytes, and we have a 4-component vector here in the position. It will be 16 bytes long. Yes. In here, in this context, in DX11 context, for some reason, it is called strides. And I don't know that reason either, but there you have it. So where can I, for example, on buffer, you have another thing here, but yeah, it's called strides. So this is basically just bytes, and it should be always divisible by 4, because that's how the video card deals with numbers in groups. I'm not really, I haven't done my reading as usual. So if you want to ask that, bother Vooks with it, and he will be so annoyed. And now he's a good guy. So yep, this is quite simple. As you have it, you don't have to deal with the index buffer usually, but if you still have it, the input assembler will actually upload it to the video card as a sequence of triangles. In the shader, you will access it as a sequence of triangles. So let me also show you how you join geometry compared to DX9. So DX9, as I showed you, you had the this and then that. And by the way, this was the only way how you create geometry in DX9. Well, how you create dynamic geometry in DX9. So there is a thing of fast. In DX11, you have a node called geometry buffer. If you want to build up from CPU, so in here you have vertices, vertex count, and a topology, which we'll also talk about later, a couple of minutes, or input layout, so which will be these fellas here, just with the join node, and obviously an apply pin if you want to control when to execute this node. So what's this topology here? In DX11, there is multiple. You are not constrained to points, lines, and triangles. So and you can't. I don't think so. In a VVV, you can even. I don't think so. In VVV, you can even switch between the two. You get just wireframe and point. Yeah, you can just solid wireframe and point. You can't really get line, as I can remember. But in DX11, you can get a pixelated line. So in DX11, you have this many topologies to choose from, which is supported, but it does not stop you. If you, for example, select this, it will not stop you to build a quad-based model pipeline if for some reason, I don't know why would you, but if you need it for some very, very advanced reason, you could do that. So it's actually this topology tells us. So let me do some commenting. So we have some theory. So we have a vertex which consists of a position. It is comment time with a little bit the vertex, which consists of a position, normal, and a texture coordinate. So we have that a couple of times. Let's just, oops. 1, 2, 3, 4, 5, 6, 7, 8, for some reason. And so we have this geometry here, which is just still the vertices, and this topology tells us that how many vertices should be grouped together in the geometry shader or during the tessellation or before the tessellation, which I will also tell you about a little bit later. So here, for example, in point list, this will be just treated individually. The geometry shader also will have just one set of vertices input for you. In line list, these two will be aligned. So let me. I will just do this. Very simple. So this will be a line, and this will be another line. Oh, actually, I will just show it in vvvv. Shall we? Let's get rid of it. Let's have a constant, because it just only requires us position and texture coordinate. So we get zip, value pin, maybe we have a 3 position and 2 texture coordinate. Couple of vertices here. Let us see. 3D. Let's have a linear spread with 10 vertices, and have a random spread. Yeah, and the texture coordinates, we don't need that, we just leave that 0. Also, okay, we will return to topologies in a second, but I have to explain a little bit about input elements. So we have this node to describe our layout, obviously. How we do that is we have 2 semantics. We can see here a couple of predefined semantics, which is a standard throughout most of the pipelines, what you get there. However, That does not mean that these are the only semantics DX11 knows about. Actually, you can use your own. In input element advanced. I can write whatever here. I can write even kitty cat. Kitty cat, and this will be a valid one. If the shader knows about this, then it will be fine. However, constant does not know about this, so it will be quite useless also in this exact situation here. But you can, I will show you an actual use case for this, which is out there, and it is good. So our position is a 3D vector, and our texture coordinate is a 2D vector. Fine, if we do that, we have 10 vertices, and we should see something like that. Whoop, whoop, whoop. So, well, oh yeah, there you go. We should see something like this. Now, okay, let me turn on the mouse on the renderer and save this into a folder, which will be uploaded, might not. Just in case. Yep. Where's it? Oh, okay. There you go. So, as you can see, normalize it. A line list topology, a list topology just describes a set of lines, or not a set, yeah, just a set of lines, and does not do any clever magic with it, as you will see on strips. So this first 2 points will be a line, and that's it. Second 2 points will be another line, and that's it. So what here there's a thing called the line strip, or well, line strip, triangle strip is a strip, which you will immediately see the difference is that it will you will actually define the vertices of that line. So in layman's term, okay, that's right. This 2 will be a line, and then this 2 will be a line, and this 2 will be a line, and this 2 will be a line. So in the first case, you've got, in the example of a line, you've got primitives equal, you got half as many primitives as vertices. However, in a line strip, you get, well, let us see if I'm right, but you get as many primitives as vertices, maybe -1. So let us check this. 1, 2, 3, 4, 5, 6, 7. Oh yeah. So you get vertices -1, primitives in case of a strip, and you will also see this. So okay, what's triangle list? It will be, let's be divisible by 3, which didn't help much. Oh yeah, because we're not caring about winding, triangle winding. Also for who's coming from DX 9, fill is not a thing. It is called rasterizer, which will tell a lot of things. So you can set this many things in it, but for now we just need this. Okay, so we've got these separate triangles here with the triangle list. If I say triangle strip, let me never mind, do something about it. So in case of triangle list, this is our primitive. So it's like 3 vertices, and then the next one is 3 vertices, and so on. Zip node has pin size 3 for text ports. Nope, it has pin size 2. So this is 2, this is 3. Actually, there's no problem here. There we go. So so this situation, what you can see here is triangle list, and in triangle strip, this is a tricky one. Let me look for Microsoft's wanted to say again too quickly Microsoft's figure for this thing. Topology. That was a very good thing, a very good explanation on other go. And image. So what happens here, this is a triangle strip, this is a triangle strip, and so as you can see, you can define a little ribbon of triangles in the style like this, as you can see also here, and this little arrow here shows the winding of the triangle. Now the winding of the triangle is actually the drawing order of the triangle on. If you have it can be clockwise or counterclockwise, and why it is important and why we talk about that is because the video card decides whether to draw a triangle or not by default based on this winding, and because this also will produce, if you rotate a triangle, this will also cause when the projection, when you project your triangle from the 3D space. So if we rotate around there, as you can see, the triangles which were not visible before, it is visible now. So that will cause a certain drawing order when you describe a back face. Now obviously we won't really need this now in this in our current situation, but we will have to give an attention for that in geometry shaders. So okay, we covered the very, very basics one. So, but we have a thing here with adjacency. So at this, I won't be able to show you the use of this now, because a meaningful. Okay, yeah, I can actually show you the use of this with line list with adjacency in my line node. Yep. So this one, as you can see on this image, is just a way of groupings. One primitive will be actually 3 primitives, or in case of triangles 4 primitives, grouped together, and the middle one will be our actual current primitive, which will be maybe rendered or not based on what we develop in the geometry shader. So let us see here. So yeah, this is as you can see, this is very self-explanatory. So here, what is an adjacent triangles, adjacent joint triangles. Now the reason why I'm not really able to demo this at this exact moment is that a meaningful application requires you a specific shader which knows how to deal with this. Obviously, Constant does not know that, and again a meaningful use also requires a pre-processing of the geometry, which will determine which triangles are near, which triangles are adjacent to each other, and create a buffer from that to represent adjacent triangles. This triangles adjacency is important most of the time in dynamic tessellation, dynamic resolution tessellation. Well, I don't have a better phrase for that now. Most of the time. And what else? That's it. Unfortunately, you can't really use this for normal, like smooth normal calculation, because you need all the triangles sharing the same vertices. So you need the different stuff for that. Forget that. This is just off topic. So okay, we have that. So this is direct extent stuff. But what are these here down there? Oh yeah, also tip for the tip here. Which one was that? Yeah, you can use a line list with adjacency. It is just the name of the. Oh, obviously we won't render it. We render something undefined. Well, the middle lines. We render the middle lines. So this one here, you can also use it to as a quad-based peep line. And again, I don't know the actual practical use of that. Maybe just a case to demonstrate that can be done. But we won't do that now, because also then you have to develop your own ways to store the models which we read in quads. That's just a complete reinventing of the wheel. We won't do that. But actually, you don't need to use this topology or any of those you don't need to use any of those topologies to just a certain thing. You can use it whatever you want. It's just a way to group together vertices into primitives and then deal with it in the shader, in the geometry shaders and tessellation. So the next one, we have this patch list, and a lot of it, like 32 versions. So what are those? So this will become important in tessellation phases. As you can see, you can control very precisely how much vertex you need in your primitive, not just by these names, but you can remember, and you have to have this picture on the hand. Also, it's just you have this. You don't have to remember this picture on your head, so you need this. However, if you use this, look at what happens. Nothing. Okay, it actually happens. But if we render as points, so because the previous more simple topologies also tells the drawer how to fill up a certain primitive. Like if I tell it a triangle is, it will fill up the triangles, and that's all right. But in control points, it won't do that. It will just draw. Sorry, that I was over scrolling, but it will just draw points for us. And if you want to use these, you have to have a geometry shader somewhere here, and we will cover that later on. So all right, we have that here. How else we do geometries? Obviously you can load couple with as imp as, oh sorry, that was the wrong one. There was another one. So wait, obviously as imp, and then mesh, and this will provide us the geometry of course. We have for DX11 we also can have direct, well, yeah, you can do direct values. I think we have nope. We have something which actually throw us the buffer. Anyway, never mind this at all. So obviously that load models, do it in CPU, and also you have a thing now which is called geometrics. And if you guys familiar from DX9 with the texture FX framework, we have kind of that in geometry. So for example, this one, and I have let's have a look at what it is. It is a shader, a group of shader, and the output of it is a geometry, and you can see it here is a stream out. And what the stream out is that our geometry in the GPU is stored in a way that the view on the data is a sequential view, so you can read that only sequentially. However, not you, but the input assembler will only read that sequentially, and you can only deal with that in the shaders sequentially. I mean, not sequentially, you will just have in your program, shader program, you will just have one set of primitive or one set of one vertex here. So the stream out gives you an overall unordered access view over the geometry data, which is unordered access view is just basically random access thing. So you can in a shader program, you can see every vertex, not just the one what you're at now. So you can have that. I don't know if this is, I don't know if this buffer is actually exposed here as a thing. It does not really, it wouldn't really help. Actually, it would help. Anyway, I don't know. I will have to ask Julian to see if that's available as a semantic. But anyhow, so this will give you a buffer that you can read the entire geometry in your shader. You can access the entire geometry in your shader program. Obviously, you won't do that because you want to read the entire geometry in a single cycle, in a single what you call it, thread, because that would be just crazy slow. So what we have here is that we have our geometry in, which we will process, and technically, so what we just used to from DX11. This is a value which you can access by semantic and enable view projection thingy. So there are a couple of switches which are quite mysterious. This as auto, I was never sure what it does, but if you don't turn it on, it won't work. So you have to turn this on. So the maximum elements is kind of self-explanatory. It tells the geometry shader how much vertex it should allocate in the GPU memory. You have, and then also you have the same kind of open layout as you had here, so we can use that. And we also have a couple of more pins here, which are generic throughout all the DX11 shaders. So you have that. I don't know if I will explain this. I don't know if I will explain this today. I might not. If I will have time, I will explain these and defines, because these are very, very powerful things, and I actually know everybody should know about these. But I mean not preliminary, but it is kind of a very, very useful thing. And you have this geometry, and then obviously you have the geometry out, which you will be able to use here, and then our buffer out. So which I just explained before, and a couple of pins which tells us what's the situation, and if anything goes wrong. So also note we have a pin called auto layout, and that is a clever one. And I will explain what that does later, because that involves a little bit of shader shenanigans going on. This part. Don't copy this. This is not really right. I will fix that. So, okay, we just close this, not to further confuse anyone. So, all right, but how about here we generate geometry out of nothing, out of values in the CPU, and we will just can do the geometry of it. But how we do that the same on the GPU? So how we can just generate a geometry in GPU, because this requires a geometry in, because that geometry in will actually determine how many times our GPU program should run. So we have a node for that, and that is called, well, okay, let me rephrase that. We have a couple of special geometry types, geometry nodes, which might not have an obvious or a trivial role in the entire picture. So the first one is null geometry, and this is a very, very useful fellow as well. Here we can set our geometry, how much vertices it should have, how much instances of those vertices it should have, and also topology, and that's it. This geometry won't contain any data. It will just iterate through an input assembler, but that's not a good phrase for it. I would rather say it will just tell us how many times our vertex shader should run, and then, well, you can imagine from the previous sayings. So and then couple it to and then couple it for primitives, and then do all sorts of shenanigans with tessellation. I will cover that as well. So we have null geometry here. I think we had another type. No. What that is? Oh yes, indeed, we have that as well. And also we have null indirect, which will look at the buffer and determine how many copy the counter of that buffer, but we won't cover buffers actually too much here. We'll cover a little bit of it because they are as well very, very useful stuff. But if you look at the buffer, and it will determine these numbers out of the size of that buffer, well, the attended size of that buffer, which is basically counter attached to the buffer. It's an integer attached to the buffer, and you can do all sorts of jazz with that, which we won't cover here because that is a very, very advanced use case. But if you need any of that, you can do that. And you have, for example, if you have an append buffer, which you can update append data to the end of it in compute shader, then you can use that in this node and then have a couple of things. Actually, there are a couple of examples for this in the DX11 girl power. So you should check it out, and it's pretty available. If you're following these workshops, you also have to have like DX11 in your vvvv, which is, and there are the girl power. So check that out because that might contain more information that I will say I've said in the previous hour. Jesus Christ, time flies by. So null indirect, that's a thing. What else? Oh yeah, and we have this dispatcher and dispatch indirect. Oh, the thing. This is not geometry in the traditional sense at all. Let's see, guys. For those of you having lag issues and stuttering, this worked for me. Or what is it? How to watch Twitch streams without lag or stuttering source quality? Okay, I will check that out later. Not today though. So back here, dispatcher. This is for compute shader. So if you have that here. Do I have a compute shader template? What sorts of compute shader have? Well, to be honest, I only use compute shader for particles. No. That's, yup. So, and a compute shader like this, because they are the same FX files as your shader here on the layer here. Actually, it's a pretty powerful pipeline to work with. So back to this. So this is one method, and there's a more advanced method. So then we have this renderer stream out, which will also give us a geometry, but instead of just a single shader, we can run as many as we want. Just how, as the renderer here, we can group together shaders and do all sorts of magic with that. I have one use case for that, and that is a node which joins geometry, which joins a spread of geometry into single mega geometry or mega mesh. Well, just into single one. But you have a higher level representation here of the input layout, because this one is actually created for 3D models and asset rendering, but there is a very easy way to develop your own. I might include an advanced option here. So that is a use case for the stream out renderer. And basically a geometrics is this stream out renderer with a single shader connected to it, and that's it. The stream out renderer works the same way as geometry shader here. So that was a lot of theory, and I hope I haven't lost anyone during that theory. Let's have a little bit of demonstration, shall we? So we create a box. Actually, we just remove it. Create a box. Yeah, that's the thing. So don't know how many vertices box have or how it is stored, but you should see nothing, obviously, because and the reason why we're not seeing anything, because the input element here is not including normals, and there are, and shit hit the fan actually here. So what we can do, I have a module here which encapsulates the input element nodes into a couple of toggles. So it is actually very fast to work with on standard geometry features. You can call these features, but standard geometry semantics. And so this is how it looks like. And we can actually turn on texture coordinate. So yeah, that's the input, texture coordinate input. Nope. Texture coordinate input. And then we don't have subset ID. That's a custom thing. Yeah, as you could notice here, this is a first use case for a custom semantic, or actually the second. This is important for iMeasure. I will talk about that on the iMeasure workshop though. So that, and let's define things, and that, oops, we have here, oh, sorry, huh, where's my cube? It should be, cube should be here. As you can see, if I turn off as auto, it will just not do anything for some reason. No idea. Technically valid. Again, a little bit of live fixing going on. Okay, I might have a problem here because DX11 updated and it became. No, actually there is texture coordinates, archive checker, called texture coordinates, and it became more strict about what kind of camera I'm using here. or what kind of layout I'm using here, and the structure going through between the shader stages will have to copy the actual layout, and I was lazy beforehand. Man, so I have to fix that for the new version of DX11 contribution, because that was allowed in the past, which is great. Hooray! Okay, I haven't realized this. In that case, demonstration comes a little bit later, and we will do our own a little bit later. So first of all, before we do our own, let me talk to you guys about don't save anything. I might have to just tell you about it. You can close this because we don't use this anymore. About shader stages, what's going on in a shader, and there was again a very good figure for this, or how our video card processes data with shader programs. So we have stages. What that does it pop up anything? Yep, that is actually a very accurate one. So this is the second figure. Let me zoom in for you. So yeah, this is kind of not just geometry. This is a more generic point of view on how things are executed. So first of all, our data arrives like this. Set of numbers arrives to the input assembler, and I will just hand over the data to this Vertex shader. So it will iterate through the Vertex shader. That Vertex shader, as you might expect, it will go once every vertex. It will run once for every vertex. Now we have like this hull shader, the tessellator, the domain shader. So this 3-1 and a couple of other things which going with tessellation. So that thing has to do with tessellation. So, okay, you might have guessed that. So this one is actually acts like a geometry shader just before the tessellation stage. So we can process our primitives there before the tessellator fixed function, and then the domain shader stage is a kind of how shall we do it? Yeah, it runs on every of the every tessellated primitive. Oh, is it? No, not at all. In every tessellated vertices, and then the last one will become a shader, which will actually run on every final primitives which are generated. Well, we will do a workshop. This workshop will be about this part here, from which part goes on from here, and then there's a special stage or special shader type, the compute shader, which is totally independent from this one, and it kind of have to run a little bit separately as well. So this is just the pipeline from the shader to the renderer, or the rest, to the renderer. So after the geometry shader, if we have a render target or an actual renderer, it will get into rasterizer, which will fill up the geometry with triangle, and then pixel shaders, which will run on every pixel of triangle, and then this thing does something which I'm not sure of what. And here, this big box here is the geometry, is the memory of the video card, and these you can read here, you can write in this stage, you can also read and write in pixel shader, and read and write in this thing, which is basically, I guess this is the one which writes to actually to the render target. Okay. So we ran through that, and most of the time in the GeoMFX, or most of the time when you deal with geometry on the GPU, you will just use Vertex shader and the geometry shader combo. Tessellation does require a couple of things. A couple of other things to do, and I might show that in the end of the workshop. So, what shall we do next? What shall we do next? Shall we... Oh, yes, forgot something. So, the problem is, we have this fella here, and let's switch back to constant. So we have this fella here with, let's have it line strip. And let us make a hypothetical situation where we need to actually read back the vertices, and we need to access the vertices here in the CPU. Well, my first comment on that is, if it's avoidable, please don't do that. The reason is, we don't need to see that. So the reason is that it requires a same kind of readback process. We can use process. Which if you remember, the DX 9 Pipette had notoriously low performance, and the reason lies in the communication, in the way how the CPU and the GPU communicates with each other. So it is possible to get data back from the GPU to the CPU, but at the same time it is also not that good. It's not that how to say it too quickly again. Not recommended. Well, this is a very custom one. So first of all, we need to convert this somehow to we need to write this into a raw buffer, and oh sorry, wrong renderer. And one way to do that is to write our very first. Actually, we will write our very first simple GeoMFX. I will clone from through, but if you don't have any accessible GeoMFX already there, you might just create a file, which I will show you. So this it should be like hello world. So okay, clone that. Okay, it turns up because obviously we didn't clone this. We will use a vertex shader, and this one, and that one, and that is good. So this should be like a bare bone of a GAMFX, a very simple GAMFX. And if we look at the project folder, oh well, if you follow this workshop, right, I know. So if we clone one, it will create a file called GSFX. If you just create a new file here or anywhere else, you can just drag that into vvvv, and it will just pop up the same way as with FX files. So like this. So let's start the very first thingy there. So first of all, we will need to have or input data. We will need to select what we will use of the input geometry. So I'll just stick with these names. Sorry about that thing. This Hungarian keyboard doesn't really work with anything else. So we will obviously need a position. You know what I'm doing here with semantic. This thing here is called semantic. That is how this. We can say that it's probably not accurate, but this is how the CPU will see this variable here, and this variable, this is how the shader programs will see this data here. This is how they will get referenced. This is absolutely not accurate though. And what else we do here? We just have position and texture coordinates, so we will have that, and the follow 2, so this is like vectors. So 3 component vector, 2 component vector, UV vector, and that's a text code 0. And then what we will do is just simply assign, simply just go through, this data should go through the GAMFX. So that's our first part. So in here we just create our output variable. We will initialize everything with 0, and there's a very convenient way to do that, like this. And then we just access the members of the structure, what we define here. I need this also. And that's UV equals input UV. Now let's see, this is a different one though, so it's not vsin. So we'll just copy it and paste it and just rename it. Now notice though that it might be a wise thing to use a different structure for a GSIN, and maybe it's a wise thing to use a different structure for the output as well. But here in vsin we can define vertex shader specific system values. Now what are system values? So for example, we can specify a vertex ID, which will be system value vertex ID, and this will tell us the sequential order, which vertex we are currently working on in the vertex shader, and that helps a lot when you want to access different buffers throughout your shaders. And also what we can access in Vertex shader is thing called instance ID. And that is a way how the GPU will actually generate multiple throw calls out of a single geometry buffer. And in more famous names, it's called instancing. And the way how you do this in VVV, I will show that later. But yeah, we have a couple of drawer nodes like that, and I won't go through all of it in this workshop, because I will just go through the most useful ones. This one and this one, which was not in the previous list because of some obscure naming reason. Anywho, this one, topology, it just tells you if you have a geometry, you can actually change how it will be rendered if you turn it on. So it will change the topology what I've just described earlier. So if you have a topology, or if you have a geometry which comes from a source which is out of your control, then topology is a very, very good node if you want to use it in the shader where you actually know what kind of primitive layer and primitive it would require, or just setting a triangular geometry output to tessellation input. You need to use topology for that. Topology node for that. So distraction off topic. Yeah, and the instance. Okay, yeah, just a little bit more distraction. Yeah. This is actually how many times a geometry should be drawn, or how many times a geometry should be processed here. And we can say a couple, well, not a couple, well, actually very lot, but you know, with the limitation of your what your hardware can do. So so this was simple. We're not really using these two here, but in this example, it's just showing that you could use those. And then in geometry shader, you see first of all these, I don't know what are these called, like properties of the function below. I'm not sure what the proper computer science theory name of this when you write a couple of properties above a function or above a class member or above anything, but here you do that, and that actually tells us how many vertices or geometry shader will pop out. And because we are awaiting in the geometry shader, we are awaiting a triangle. Also, you can await a point attribute. Thank you, Tom Film. And so attribute. We'll just do this. And so here, yeah, you define how many vertices your geometry shader will pop out, because you can pop out a limited number, but that is, I think, wait a second, what that is. Oh, oh yes, that's good. Actually, there's an error if you over define this, so you just be careful with this. But we will see. Okay, we will go back here after a while. And then we can use line, and we can use triangle here. Let's just stick with that. Well, actually, let's just stick with line because we have like a line and a 2. We have a line strip and a 2. And geometry say that in line has 2 vertices. And then we will have a line stream. So this will be our stream object, which we can append vertices to. You will see that, for example, in this stage, we can choose whether to append or not a vertex, or even how many vertices we can append. So this is a very, very clever thing. You can actually filter out primitives with this one. So let me do some preparation here. So we have an output again. Well, actually initialize this. And then because we're just kind of going through it, we will do a for loop, a pretty simple one, and then, oh yeah, sorry, I got used to 3 because most of the time I work with triangles, obviously. So, yup, and then O equals inputs I, and that also GS out. I think gets append. Oh, and if we want, this is a stream, and well, that's actually a strip. Okay, as you can, so what the output of this, the topology of that will be actually a kind of a strip in the behavior. Well, you might have noticed there is a couple of there's not so much consistency between the names. Anywho, if you don't want your string, if you don't want your geometry to behave like a strip in the current primitive process, on the current primitives, so this won't convert actually your geometry to a strip, but the entire geometry to a strip, but it will, you will see, because we will do some magic with the lines. Yeah, we will do some magic with those lines, what you can see here. And just to be safe, we will say these. That's a strip. I have to look that up. I wanted to click the other one. Now I have to wait. Oh Jesus. He's not on top of the situation today. Let's see. Yep, restart strip. Okay, there you go. There. And last stage, so we have these two, and then we will have a stream out. Actually, for this case, we can just leave the geometry shader out and that will be cool. However, we won't want that because we will do bits with this geometry shader. So here on the stream out GS, we can have like we can construct this thing, a geometry shader stream out object, and the way how you will define an output layout for this is via a string, and that string should contain your semantics. Come on, position, and how many components that semantic will have. So the vector and text code 0.xy, because that's a 2D vector. Yeah, sorry. Obviously, we will have to return here our vertex, and we, in theory, are good to go. So let me just also show you the matter message. Oh, come on, what's that number here? 1000? There you go. So as you can see, here, so here a geometry shader can't output more than 1024 numbers, or is it? Or what else? Scalar components output to data 5 equals 5000. I'm not really sure at this exact moment what that means. Oh yeah, sorry. So that's 5000. That's why it can be did. That's it. It can't output more than 1024 values or numbers. Well, it's colors, as you can see here. So in case of a triangle, in our case, that is only so there's 5 values. Yep. We can just Jesus. I would just do the math here. So like 5. Not really good with computations in my head. So yep, we can only, with this setup, we can only have 204 vertices coming out of the geometry shader. So that's the thing. And obviously it should be also it's per vert. I think it's per vertex. It seems to be per vertex because we have 5 values here. I didn't complain about the numbers here as well. Here. Yes. It's obviously per vertex. Come on. Sometimes I'm too dumb. I feel too dumb for these workshops sometimes. Anyhow, that being said, if I've done anything right, yep. If that obviously we'll see this because we've done this. We know how many elements we have, and. Okay, yes. Don't know how many elements we have for some reason. Seriously, why? Okay, yeah, sure, alright. So, reason why we don't know why we have this behavior. This, so not the war geometry was rendered out, because line strip. Okay, so we have, if we just do this, notice if I turn this off, turn the, where's the enable? That's the proper way to turn on and off geometry. So if you turn on off, nothing will change, because the output of the line, the output of the geometry will be a list. Whatever you see here, it actually will be a list. Oh, hello. Hello. I was some bugger. Okay, when was the last time? Oh, Jesus. There was some discrepancy in the streaming, and I'm just reloading now if I can see what that is. Huh. Did you guys see a freezing thingy here? Okay, now it won't really. Oh man, what's the chance here? Someone is nasty. Something is nasty here. Anyhow, can you guys actually hear me? Nope. Yup, you can hear me. Okay, that's the thing. Can you see me also? Because I can't see myself. It froze for a bit right before connecting. You're not. Okay, that's cool. Everything is fine. Why I can't see my? Okay, never mind. I can see my own stream. Anywho, the video is back now. That's amazing. All right, where were we? If you can see the guys. Okay, cool. I can see myself as well. Everything is fine. So back here, and where were we? So do you guys remember the thing? This is all awkward. Let's put this here. So here. So as you can see, our triangle list will, triangle line. So our line list, we have the same amount of numbers here. Our line strip, we have different numbers, and the reason is that the output of this geometry shader will be an actual line list, not a line strip. A line strip will be converted to a line list. So to fix that, remember we had, in case of strips, I will just delete this. Oh Jesus! What the hell? High encoding. Oh yeah, I have a message here in OBS. High encoding CPU usage. Oh man. Encoding. Come on! I've said NVIDIA. I set my graphics card to encode this shit. Nasty thing going on. I've closed that thing as well. Just a second, I will fix it. I hope it will fix it. So okay, back to topic. So remember how many primitives we will come with the strip. It's how many vertices we will have, and -1 times 2. Because we have 2 vertices in the case of line strip. We have 2 vertices per primitive here. So the maximum element will be 22 in this case. obviously, if we say line list here, then the value will be just the same as here. So, oh Jesus, okay. That being said, okay, video will be get freezy. We'll just turn this off. Boom, goodbye. Yup. So, nope, video will get freezing. I don't know. It looks like today the computer today is just very whiny thing. Sorry for the freezing video. It might. Jesus. This is ridiculous. Anywho, back to the topic. Back to our original topic, which was. Sorry for jumping around, but okay, we have this very simple shader here, and then for some very weird reason, which is very rare, I hope, and you should absolutely not do this, but for reasons, for example, one use case when you validly can do this is when, sorry, you need this one. Is when you write, you want to write your geometry to disk, because surprise, there is no dedicated node for that with DX11. You have a dedicated node for that in DX9, so that's write mesh EX9 geometry, but I think instance noodles comes with an OBJ right there. Yup, nope, that's something different. Anywho, so you want to write that on disk. So how many strides we have here? Also, we can calculate how many strides we have. Yep. Input element split. Just actually do the proper way. Also, this lot here will eat up a little bit of CPU cycles. As you can see, well, not a little bit, actually a lot of CPU cycles, because it might also use readback, I think. It might also use readback. So you should definitely not use these at all, or just for a couple of frames when we're writing. So that being said, how we can determine it. Oh yeah, we can determine by here. And what was the node for that? I have to look that up. No layout. And there's this here class format. Oh no! Jesus Christ! Don't say anything. So we have that finally successfully copied that node and the string. Yep. So we've got the size here and nodes, and size of that is it's 20. So we have that buffer here using a readback, and we should define a layer here. I will just add floats. Yup. And we will have actually float 3 and float 2. Yup, we can have separate values here, but if I set sorry for the video guys, it's just like crazy nonsense going on. I could just set float and then it will output all the values here in order. And notice how many CPU cycles it takes. It takes a lot. It can slow down severely your project, so don't do that every frame unless you really need it. If you need to do that every frame, you might reconsider your methods. So and then what? Actually, you know what we should do here is represent our values as unsigned integers, because that will actually keep our values intact of any kind of rounding errors or any kind of casting to double, because we works with double and all sorts of jazz. Seriously. Okay guys, just a second, I will stop streaming and yeah, and start stream again. So let's hope it works now. I don't think so. I hope. Oh Jesus. So let's roll. Value unsigned integer 32 bits. Here, that give a nice little data as raw bytes here of the geometry stream out, which is also huge. Well, not that huge, but you know, you can imagine. And then, ooh, Facebook notifications, okay. And then, this is ridiculous. This is why this stops? What the hell is OBS's problem now? This is ridiculous. And I had way much better load. Crap. Jesus. So we should need to find the right row here. That can come here. This one, we'll write it for like row data, so row down, and then write it. And if we look at here, we have a 1 kilobyte file. Huh. Will it open it as hex editor? Okay, just a second. I will look up on my CPU usage, because programs are not opening as fast as usual. Holy Jesus! Let us see, just like that. Hey. What's this? Smash OBS. It doesn't eat up that much CPU. Why is it? Well, okay. I might just stop this. What happens if I just quit? Okay, you can see this is bullcrap. So anywho, you will tell me, guys, when it's frozen or not streaming, because currently I was too lazy to set up a control computer, and it looks like whenever I was downloading the same stream on my second computer, it just froze everything else. Twitch.tv. There is something. Anyway, this little intermezzo we had here. So unfortunately, with this file saved, we don't really have any kind of idea what does it still have? Yeah. What the structure of the geometry actually was. So you might write it to a method of the file next to it, or you might work out your own thingy, or you actually look up a format specification on the internet and copy that. Basically, OBJ is pretty easy to implement actually, and it is readable back with ASIC. Oh well, actually, nope, we won't do OBJ now. We don't have time. So, same time. Let me just open a beverage. Oh, I was thirsty as hell. So, we have that. And let's presume we just know, or trying this one. Instead of generating here, happy application. Instead of generating this here, we can read it back. Read a row. That this will happen as value and single. Just remember we had 32 bits. Was it? Nope. Not at all correct. Oh yes, it was actually correct, because we have line list here. This one. How many vertices we have can be actually determined by the length of row And of course, this is not how many vertices we had, but because this is bytes, this is now many numbers we have here, and this is how many components we have here, 5, and we arrive at 22. Number of numbers per vertex, and obviously number of bytes as color takes up, a floating point takes up. We have the same input element as here, and if I get it, booyah, same thing. So I've been frozen for like 10 minutes. Sorry about that, guys. I hope it wasn't that bad of an information loss. Anyhow, this thing happens here. All right. Let me also think a little bit. So, okay, next step. So this is how you save or manage around your geometry to the disk and then load it back if you are working with your custom pipeline. Of course, if you want to save out your geometry in a sense that, in a way that other software will be able to read it, because in this way other software is not guaranteed to read that thing, then you have to find the specification online, as I said, and mangle around the data until it meets that specification. And I suggest to mimic OBJ or OBJ for that, because that supports, well, because that supports a reasonable amount of vertex features, like texture coordinates, tangent spaces, per vertex normals, etc. I'm saying that because you will be surprised. Sorry. Is there any way to save, read animated geometry, such as Kinect video? Okay, let me finish my sentence and I will respond to that. So, the reason I'm telling that, because not many formats is actually knowing that features. For example, STL, which is rather used in 3D printing, not in graphics, does only know per triangle normals and not per vertex normals and nothing else. But it's a very, very easy format. It is actually the easiest formats out there. Now to Vasquez's question, animated geometry. Problem with that, with animated geometry, is if you have, for example, like with Kinect, if you have a generated geometry out of a Kinect point cloud, then, and the problem is it will turn up, I think it will turn up as a huge geometry, like let us see, is it times, and I think this is the resolution. So that we'll have 123,904 vertices, and if you, let us see, that you might want to save out positions, which is 3 components, with normals, which is 6 components, and then texture coordinates, which is 8 components. So this is the numbers, and then multiply by 4, because these numbers are all 4 bytes. You will end up with this size, which is not, which is 3 megabytes per geometry. This is also, you can calculate this way how much your geometry will take up on the GPU, how much space it will take up in GPU memory, roughly. Probably it will take up more because of the metadata and all that jazz going on. But also, if you want to save out animated geometry, what you might do, actually, let me test that. So we have that, and with the time, so that's cool. And so this is driven by our CPU. But obviously, for an animated geometry, you have to save out every stages you have, every frames. That's the most simplest and naive method to do that. You can do any other more clever methods, but any other cleverer methods that require a lot of additional things to do. So actually, let us record a couple of geometry. I will just do that. And remember how we done this. Read back. Road. Set this right to 4, so we know all the floats. It will take up just the unsigned integer as row, and that obviously it will do this, write a row. Also, this way you can obviously send out your geometry to other computers or things like this. So you can do whatever you want with this, but we will just write it to disk. And let me have a counter. And that's oh Jesus, unlimited format value. Just a couple of hundred clicks later, we will have a thing. Oh, sorry. Geometry frame. Yep, that's leading zeros. Yes, characters before comma 5, because why not? So we will finally have our file name. Things might happen, and so we have our moving geometry here. We got this bit. I don't know. Okay, that is enough. And as you can see, we have our recorded geometry here. And so you have a couple of options here. If your geometry is not that big, as you could see here, then reading that back, well, reading that back is just actually a div to that this RAM counter plus sorry, get slice. I don't know why did I have that plus in my mind. Slice is a string. That and I want to play it. Don't know what will happen. We have another one. And as you can see, we're now reading from the disk. But obviously, if you have a big geometry, so we have like we have 22 vertices. That is nothing. So most of the time you will work with thousands, 10,000s, or even millions of vertices. And in those cases, this is just a proof of concept. For those cases, this framework would not really scale. That you might want to do some more clever thing. What you can do is that you can buffer up. Well, I don't know how, it depends on how long the animation. For a short animation, you can load the whole thing at once in your loading phase of your application, and store it in memory or even on the GPU memory, and then use a very clever compute shader or a very clever geometry shader to read only a part of that buffer. So it will represent your actual geometry. But yeah, for a Kinect point cloud, because you can save Kinect point clouds like this, if you fancy. You might be. You see, the CPU way of doing that is not too feasible. Yeah, it's not that wouldn't be too feasible. So you have to do. I won't have time to do to demonstrate that now. Maybe in person, if you'd like to, you can contact me if you need a situation like that. But I can help you. But now is not the time to do that, because that's a couple of hours of working. So let us get back to actually the geometry shaders. So now we will jump into some funky business. I will just leave it here. And before we jump into, sorry, I'm really thirsty. So, okay, so I told you right here we can filter out or append more vertices than what we actually have. So, for example, let us do some filtering. We have a special semantic, a special system value called the ID called SV primitive ID. And we can just add that to the arguments of our GS function, or geometry shader function. And for example, we want to only append every second line, which PID to equals 0, then this should happen. This did not happen. Oh. Let me just put the for loop as well in the if condition. Wow, why did this not happen? Anywho, it never equals 0. It always equals 0. Why it always equals 0? That's it. That's a very good question. Well, it's confusion time. Or if one thing which we can test with is if I will calculate length of our line. So line length equals distance from input 0 from the first vertex to the second vertex. It might no, because it wouldn't actually run. Does it run? No, it doesn't. It doesn't run. Okay, never mind. So just a second. I will Google this. And this is completely valid stuff, so I don't understand why I'm not getting proper primitive IDs. Yeah. Anywho. We want to need this for them. Input 0, input 1, push. That's if hello is let's see, should we draw small lines or big lines? We should draw big lines, and let's have our variable here. Draw threshold equals that, and threshold. This happened. We should already see lines disappearing. Come on. What the heck? It's something that there is something I'm not thinking about here. What that possibly could be. That is hilarious. Tough. Today is again a day which is nothing works. Do we have this even connected? It's turned on. Jesus. I don't know. If anybody has any idea, I would appreciate that, but to be honest, I don't know why I have this. I don't know why I don't get lines disappearing here. Jesus. Okay. Now it is time to get girl power here. Vertex 11 girl power. Where is it? So, girl power. Some 4. This. Where that was. Maybe this one. Oh no. Nope, not at all. However, notice this is a very, very good example though. Which was the other one? On the stream out. I think this was the one. Okay, yep. Sphere map, box, better, tube, better. There you go. There you go. I don't know when I'm opening everything. Does the same. Anyhow, this is a very good demonstration here in itself. This is just in the girl power. You can actually filter out if seriously, Jesus, I don't know why I'm not getting disappearing lines. This is bullcrap. But yeah, you can do this. You can see this here, and if you put it in condition, then you can just filter out lines or filter out primitives. Anywho, let's get back to our not so well working example. Come on. It's why? Seriously, mate, I don't have any idea. Anywho, let's try appending one, shall we? Appending one under there. If it doesn't work, appending another one. Then we will just call it a day, I guess. No, we won't call that a day. There's so much else to explore. For example, tessellation. We might cover that. So let's go to what should we? Let's duplicate one. Let's create a continuation of one line, or not, but say another line. So we will just do that. So input. We will have like 3 dir that minus that, sorry, and then append a new position. Let's append the original one. We will create a new one. The new push equals this plus there. I hope, and then just up and down. Yup. Mine is there. Nope. Okay, we have now problems. We have now serious problems. It does mean that we deep line statistics. It does mean we have some problems either with the geometry shader. There you go. That was not on. Why? This was not on. See that? I don't know what's the meaning of that pin. Anyhow, there we have this geometry shader invocations. Amazing, marvelous. Anywho, that happened. Oh, yep. It's just this. And okay, now the trees. Yep. And also this. And now we are in trouble. We are in serious trouble here. Again. What the hell? Oh yeah. I forgot. Actually, we just do this dot push. And there you go. Okay, there you go. So it works. This is now on, and because now we emit another geometry, another vertex, so we can say ×2. So we can say that this many primitives we will have, and we will so ×3. Nope. Yep. So because we will have 2 extra lines, we have to have 2 extra vertices here. So that's the maximum element should be raised by 2. If I'm correct, maybe I'm not. Anywho, so we can do just like that. Of course, oh yes, another mention on this pipeline statistic things. So you can actually look into how many times your shader program has ran, and the other thing is that it does use the same kind of readback as you could see when we were saving out the geometry to the disk. So it can slow down your workflow. You can slow down your entire patch or project. So then you can. I recommend you don't use these values here in any other way. Use this only for debugging, but nothing else. Anywho, now what shall we do here? So we were just working with lines. We were working in lines because it's actually quicker to render and quicker to work with than with triangles. However, with triangles, I will just show you some pre-made stuff like this extruder. Now this one actually requires a proper geometry with proper data, so we will use a box. From directional, yep, it doesn't have stuff. Whoopsie. Oh yeah, forgot to turn on depth buffer, and obviously my normals are totally messed up, so don't listen to that, and you will actually learn something why my normals are messed up there, because of triangle winding, and I don't have the right winding because I didn't care when I was calculating. But oh, sorry. Okay, I hate this. Don't need that. No puns. Fucking bloatware. Seriously, Jesus. So here it can be used, for example, to more oh yeah, I will tell you what that ugly thing is there in a second. So it can be used for more advanced effects like this. This is very simple, but for example, you can generate grass from it. Well. Yeah, grass from it, to have just a couple of starting point, and then grow some little lines out of those points. You can do it in Geometry Shader. Also here is the reason why you see this clipping thing is going on is that my extrusion does not care about adjacent triangles, adjacent geometry. Actually, it won't show up if I will use a sphere instead of a box. There you go. It will just have weird things over here. And the reason for that is that sphere has a couple of extra triangles for actually making it easily texture mappable. So this is not the best sphere, so there you go, ecosphere. It doesn't have that. Now there you have it. This is perfect. Okay, it's far from perfect, but you can see. So you can actually, in our case, to 24 with this many values. I'm sorry. 24 vertices with this many values. If we calculate that, this is a 4 component value. So that is like 3, 6, 8, and 12 numbers, and it's already 288 numbers out there. We could add make it a couple. Let's see how many. Okay. User interface glitch. Oh yeah, we can add like 3. Yup. 3 more. 3 more levels of this, which that maybe, and then we are running out of 1024 triangles. And also this geometry shader program, you might notice, does not append our original triangle to the bottom of it, which is it's not good. I mean, it should. Well, it says bottom. But it's okay. I know why it is not doing that, because I have a bug somewhere, and I was not smart enough when I was writing this to overcome I was just basically not smart enough. So yup, that's geometry shaders for you. Okay, let me just show you what you've seen in the intro, and that will have some clutter around it, but okay, let's just jump into that. You've seen that in the intro. That was at places. Because in that intro, I like to show you how tessellation works. So, interview starts up. I will have a sip. So I've got something into my mind. Oh, yep. Sorry about that. I had to move my microphone a little bit. Shooby-dooby-dooby-dooby-doop. So we will see some couple of eye candy next to our geometry as well. And we don't need that much resolution. We don't need that window. We don't need that either. It just goes on up. Okay, it does work a little bit slower because of I'm using the GPU for decoding the video or encoding the video as well. We don't need these splines either because that is basically instance noodle materials. So what's going on here is we have a file which contains our letters, as you will be able to see. I go into Scene Explorer, so that letters were done in Blender. As you can see, here are the letters, Notice they are not in order, so I had to make some shenanigan to get that in order. And we have our before mentioned join geometry here, which also there are some mesh specific defines here, and which will make our spread of geometry a single one, so we can, because geometrics are not spreadable, we have to actually make this to happen. And there's a subset ID, so we can we write a subset ID as well, so we can access different parameters from buffers. Now, well, a couple of words of buffers in DX11. If someone is not familiar with them, in DX11 there are the two types of general purpose buffers. The first is structured buffer, and the second is a byte address buffer, or in vvv's context, it is it's called row buffer, but in shader it is byte address buffer. Sorry. Now the difference between the structured buffer is actually an element of that. So these are basically just a huge array of numbers most of the time. It doesn't have to be huge at all. So it's an array of numbers or data. Sorry. Yeah, most of the time numbers. You can't actually have different things. That's numbers. And where was I? Oh yeah, it's a structured buffer, and it's basically a structure like this one. So this whole thing can be put into structured buffer, obviously without the semantics here. And one element will be the structure of one element will be the structure of this, and then one can be generated by the dynamic buffer nodes, which are typed for you here. You don't have like a general purpose one, so if you have a structure you have to like code it yourself. Right? And the other way to have one is through or buffer renderer or buffer renderer advanced, which lets you do any other jazz as well. And here you have to define how many bytes one element you will have, and then you can access how you access it in shader is the way like this. So you have the structure buffer and your type. Now the type can be a built-in scalar type, like here for float 4. I was lazy to develop my own structure for this application here, but you can actually write in here the name of the structure like that. Obviously it won't work in this shader, and then you can access the members of that structure like with the dot notation, like this one here, the dot notation. So here, and that's a structure buffer, and the byte address buffer is a little bit more advanced stuff in the sense that you have to address individual bytes. Now obviously, well, not obvious. That's not obvious, but naturally, because it's not naturally either. So the thing is that the GPUs can only access 4 bytes of that buffer, and the bytes address what you want to access is also have to be divisible by 4 because the numbers what you store on the GPU is most of the time are 32-bit, except for pixels. Yep, except for pixels. And then when you use half, or newer NVIDIA GPUs can do double as well, so like 64-bit numbers. But in graphics, you're pretty much good with 32-bit as well. So that being said, backtracking a little bit to here, why it is good to have like 18 geometries joined into one, and then have a subset ID. Then I can set different values for each of my subsets. For example, here I can set, if I just move this, then I can set I will use a magic number here for the sake of simplicity. You can set different values so I can set different values for the individual subsets. So now I'm manipulating only a single geometry. What the jizz was happening here? Oh yeah, that's just the lighting. Yeah, strange lighting. So now I can set individual subsets with transforms, if my shader supports it, of the geometry. And yup, with different transforms or different values. So that being said, what happens in this tessellator node? So here I'm also having a texture here, which will be covered next week by Idvir. I don't know how to pronounce her name or her VVV name. Anywho, so we have a couple of randomly generated parameters here and that. Blah blah blah. So that shader, what it does, you have a couple of spheres, and then it will explode and extrude vertices along those spheres. So like that. Okay, I will turn off this rotating shenanigan. That. So it will explode. It will explode some vertices. From basically it just plays as an attractor, and then I can set a couple of values. For example, here I'm setting a couple of values for the extrusion part individually. For letters, it goes in like a wave shape through the individual letters here. And what else it does? Yeah, it does a little bit of extrusion, what you've seen before, and that's it. So and also it tessellates our geometry based on a texture, and that texture is here. So now notice that for tessellation, here I'm setting the topology because our code requires 3 control points. I will set it at 3 control points, and also have to convert it back to a triangle list because no reasons. I mean, yeah, because otherwise it will stay as batch list and it won't render correctly. I'm not needing this. That was my lazy attempt for generating the previous position, and now I have to generate it manually here inside this monstrum. So for tessellation, we need I will be a little bit skippy on this, but we will need these structures. These structures are the communication between the different p-pline stages, and a couple of functions I have there. We need a constant function for Hull shader, which will determine how many triangles or how many subsets, well, how many other primitives we have to generate through on the GPU. And also we can generate here, for example, this one is the PN triangles from Microsoft, which was implemented by vooks into vvv, and so that is okay, let me just slow down there a little bit. Okay, never mind, I won't slow that down. So that is yeah, it determines how many vertices how many primitives we will have by setting these numbers, and those numbers are, if we jump over here, is the test factor for the edges, and the inside test factor for the inside of our primitive. I'm saying primitive and not triangle because you can tessellate, for example, a quad, or you can tessellate a line as well. So anything. In the line's case, you don't have to have an edge. You just have to have a test factor. You don't have to have an inside test factor. Anywho, and then we will get also for the in this function, I think maybe that is nope. Also in this function, if I know well, no, you won't need that. Yeah. I think the constant fixed function will generate you the polycentric coordinates. Anywho, yep, this is constant function, and then we will have Hull shader. So in this Hull shader, it actually acts like a geometry shader before the tessellation. So in this thing, which is like this. Let us see. Yep. Oh no. Sorry. But it's not quite the truth that it acts like a geometry shader, because you can't append or remove or filter out vertices here. You have to actually return every single vertex what you have here. So you don't have that much freedom, but you have access to all the entire primitive. So you have access to the entire current primitive here, as you can see, and you have to, like, SV output control point ID. You get the actual ID what it is working on currently, and as you can see, also you have to set your attributes here on how your geometry will be tessellated, and you can look this up on Microsoft MSDN. I won't do that now. I won't list that now. Most of the time, if you work with triangles, this is okay for you. But yeah, you can do so much other things with it. Anywho, here you also define which is the function, which is the constant function you want to use. Like here, it's AHSC. in all case, and then our output control points, which is, you know, output control points for the tessellator. And so clockwise, and then here, yeah, we have the partitioning is fractional or the functional even. Or there's two other types, which is not that nice. Yeah, that is an integer, and I think there's another type which I'm not sure. The difference between these is that you want to divide your triangles into an even number of. You want to divide your primitives, or not triangle, but if you want to divide a primitive into an even number of equal parts, not equal parts, well, fractionally organized parts. Well, that's obviously not the correct thing. Can I? Actually, I'm a little almost turned off. Maybe. Oh yeah, I was turned off because I was testing that out, whether it was the source of the slow CPU thingy. Anywho, that turned out to be Twitch TV for some indescribable reason. So back to this one, the fractional or an even number of odd or an even number of equal parts when the numbers are a whole number. If it is not, then it will do a nice fade between that. And then obviously from this workshop you won't learn anything about shaders though, but it might be a good or a frightening introduction into that. And then you have a domain shader, which is like what you do with your generated points out here. And patch. So yeah, we have the patch. We have a control points here, which, well, to be honest, it's a little bit of black box for me. What happens here? But most of the time, it's just for triangles. You get a barycentric coordinates, which is like a weight of where the actual coordinate is, and then you generate here your numbers, your vertices here, and that, look it up on the internet. Sorry about this. It's a little bit of black box for me here. Anywho, like this, because I haven't done my reading properly and I don't remember now. Well, so here you actually, what you return here is the actual vertex, which will then better go to geometry shader or pixel shader. In our case, it will go to a geometry shader, which will do extrusion, which I won't cover how it works here. It's pretty simple. It's just a lot of manual twiddling with geometry. And what you've seen before with the normals, here, as you can see, I calculate here normals here. So yeah, so here, and I mess up. I don't really care the order of the winding of the triangle here. So another triangle will have a flipped normal like this. I will actually, at this point of video, I will just probably have a link on the YouTube link box, which will point you to a very, very good video about how this works, what this actual triangle winding is, because I am absolutely not able to tell you that better than that video. And Yup, we have that. Why I'm not restart stripping here? Interesting. Anywho, we have a simple geometry shader which didn't do the that, and then what you've got here is the layout here, and obviously my technical declaration: the vertex shader, hull shader, domain shader, geometry shader, and then a stream out. What did we change? No, it was perfect. I don't save it. So this is a geometry, geomfx. Give us a geometry, and whoops, and where was it? And it is then guided and then directed to MSF, which I won't cover now. But this node, for example, awaits a geometry which has a subset ID. So it is like a join geometry. So you can assign different textures from a texture array to that geometry, and then define different parameters here, which will I guess it will be overhauled a little bit in the future. So yeah, I won't cover the remaining part of this patch. So that's for tessellation. Oh yeah. I said about the texture-driven tessellation here. Here. Oh, what was that song coming out of my head? Anyhow, it is actually driven by the distance from our virtual sphere, virtual attractor or whatever, which we have there, and then our texture, we just multiply together, and yeah, we can have multiple spheres. Doop-a-doop-a-doop. Yeah, we just multiply together here, and I can just set tessellation here, and I'm reading the texture here. By the way, that texture it doesn't really look anything from the point of view, but it is a simple plasma noise. And so that, also we have a frame delay here and an RGBA, because I'm also using the previous frame texture to have nice motion blur effect on the thing. So okay, I would also like to talk to you about this node, because actually I was talking about this node. Anywho, this one, I will talk to you about this node on the MSF workshop, which will be in the end. Actually, it will be before Christmas if everything goes wrong. Goes right. If everything goes right, it will be before Christmas. I'm still have to improve my speech skills. Okay. Anywho, what I haven't told you about geometry, about a lot of things, but you get the point now. I guess you get the actual point after this workshop, how the geometry works in DX11. I hope. I don't know. If it does, if you don't get the point, just contact me, because for certain situations you will. I'm pretty sure that if you will not save it before this point, you will have questions. And to be honest, as you've seen that I had I had another difficulties here. For example, that one I haven't noticed the as auto was not turned on, which I'm not pretty sure either what that as auto does. Probably I will ask Brooks after this one and just note under the video. But anywho, so that's it. That's the thing. And so I hope you like that, guys. And I hope it was useful. I have. It was definitely useful. What I've said on the beginning of this one is that with those two very weird things, the semantics. Well, you can declare your custom semantics there in DX11, and then you can just assign it. It's pretty good stuff, actually. I will be able to show you that. Just on like this here for some reasons, so for some optimization, I'm assigning textures to the shader via semantics, and you can do that here with resource semantics, because the shader node doesn't have that. Or in case of texture effects and geometrics, blue is okay. You can connect those here to these two pins, which are hidden by default. And in case of layers, you have to connect to a semantic node, like this one. So that I call this a day. Yep, I'm calling this a day because I kinda don't have too much idea now what I can tell you more about geometries. Yep. More stuff coming on the next 3 workshops. So, actually this was our intro, so I will just let's do this. Look. So, guys. See you next week. Next week, it will teach us how to pixel shade. Maybe a little bit, not a little bit, maybe a lot better than I've done with geometry. I don't know. I will plan a compute shader at some point. Maybe compute shader will be covered with everyone is happy on instance noodles. So we will do that, and then we will actually learn how to use MSR at the end of this whole thing, and we will have a proper Christmas. Yay! So that is the thing. Okay, guys. See you next weekend, hopefully, and have a good day. Bye. Stop streaming and stop recording as well.